Hello friends! In the last video, we built up the intuitive idea of a limit. What it really means when we say a function approaches some value as x gets closer and closer to a point. But intuition alone won't help you solve problems on paper. So in this video, we're going to learn how to actually compute limits. The real techniques, the ones you'll use again and again in calculus. We'll start with the simplest method, direct substitution. Then we'll see what to do when substitution breaks down and gives you something weird like 0 over 0. We'll cover factoring, we'll cover rationalizing, and at the end we'll quickly look at what happens when x runs off to infinity. By the end of this video, you'll have a clean toolkit. When you see a limit problem, you'll know exactly which tool to reach for. Let's get into it. Alright, let's start with the easiest tool in the box, direct substitution. The idea is simple. If you want the limit of a function as x approaches some number, just plug that number into the function and see what comes out. That's it. Look at this example. We want the limit of x squared plus 3x minus 1 as x approaches 2. So we substitute 2 wherever we see x. 2 squared is 4, plus 3 times 2 is 6, minus 1. That gives us 9. Done. That's our limit. Now, here's the rule of thumb. Always try direct substitution first. For polynomials, for most well-behaved functions you'll meet in calculus, substitution just works. If you plug in the value and get a clean real number back, congratulations, that's your answer. Move on. But, and this is where it gets interesting, substitution doesn't always work. Sometimes you plug in the value, and you get something strange, something undefined. Let's see what happens then. Now look at this one. We want the limit of x squared minus 4 divided by x minus 2 as x approaches 2. Let's try our first tool, direct substitution. Plug in 2 on top. 4 minus 4, that's 0. Plug in 2 on the bottom. 2 minus 2, also 0. So we get 0 over 0. And 0 over 0 is a problem. In math, it's called an indeterminate form. That's a fancy way of saying we genuinely don't know what this equals just by looking at it. It's not 0, it's not infinity, it's not undefined in the usual sense. It's a signal that the function is doing something interesting at that point, and we need to dig deeper to find out what. Think of it like opening a file in Word and seeing file corrupted. Word doesn't crash, it just tells you the standard reader can't handle it, and you need a different tool to recover the content. 0 over 0 is the same idea. Substitution can't read this one, so we switch tools. The good news? There's almost always a way to rewrite the function so the problem disappears. And that's exactly what we'll do next. Alright, here's our first real technique, factoring. Same problem as before. The limit of x squared minus 4 divided by x minus 2 as x approaches 2. Substitution gave us 0 over 0, so we need to rewrite this expression. Look at the top, x squared minus 4. That's a difference of 2 squares, which factors into x minus 2 times x plus 2. Now look what we have. There's an x minus 2 on top and an x minus 2 on the bottom. They cancel. And that's the whole trick. The factor that was causing the 0 on top and the factor that was causing the 0 on the bottom, they were the same factor. Once we cancel them, the indeterminate form disappears. Now we're left with just x plus 2. And on this simplified version, substitution works perfectly. Plug in 2. 2 plus 2 equals 4. That's our limit. So the recipe is, factor the top, factor the bottom, cancel whatever's common, and try substitution again. Works almost every time when you're staring at a polynomial divided by a polynomial. But what if the function has square roots in it? Factoring won't help there. So let's look at the next tool. Alright, here's the next tool, rationalizing. Use this one when you see a square root sitting inside a 0 over 0 limit. Look at this expression. The limit of root x plus 1 minus 1 divided by x as x approaches 0. If you plug in 0, root 1 is 1, minus 1 is 0 on top, and 0 on the bottom. Classic 0 over 0. Factoring won't help here because of that square root. So we use a different trick. We multiply the top and bottom by something called the conjugate. The conjugate is just the same expression with the sign flipped, so root x plus 1 plus 1. We multiply both numerator and denominator by it, which is the same as multiplying by 1, so the value of the expression doesn't change. Why bother? Because when you multiply the top out, the square roots disappear. Root x plus 1 times root x plus 1 gives you x plus 1, then minus 1. So the top simplifies down to just x. And now we have x on top, and x times that conjugate on the bottom. The x cancels. What's left is 1, divided by root x plus 1, plus 1. Now substitution works. Plug in 0. Root 1 is 1, plus 1 is 2. So our limit is 1/2. The pattern is the same every time. Square root in the way, multiply top and bottom by the conjugate, expand, cancel, substitute. That's it. One more technique to cover. What happens when x doesn't approach a number, but runs off all the way to infinity? Last technique, limits at infinity. This is when x isn't approaching a normal number, but heading off to infinity, getting bigger and bigger without stopping. Here's our example. The limit of 3x squared plus 5x divided by 2x squared minus 7 as x approaches infinity. If you try to plug in infinity, you get infinity over infinity, another indeterminate form. Substitution can't handle this either. But here's the key insight. When x is huge, and I mean ridiculously huge, like a trillion or a quadrillion, the smaller terms barely matter anymore. 3x squared is a gigantic number. 5x next to it is basically nothing. On the bottom, 2x squared dominates, and that minus 7 is invisible at that scale. Think of it like sorting files in Windows Explorer by size. If you have one file that's 50 gigabytes and another that's 2 kilobytes, when you're talking about total storage, the kilobyte file might as well not exist. That's how the lower power terms behave when x runs off to infinity. They get drowned out by the dominant terms. So the shortcut is, keep only the highest power on top and the highest power on the bottom. 3x squared over 2x squared. The x squareds cancel. We're left with 3 over 2. So our limit is 3/2. That's the value the function settles toward, as x grows forever. And with that, we've covered the full toolkit. Let's wrap it up. Alright, let's bring it all together. When you see a limit problem, here's the thinking process. Step 1. Try direct substitution. If you get a clean number, you're done. Move on. Step 2. If substitution gives you 0 over 0, look at the function. Polynomials? Factor the top and bottom, cancel what's common, and substitute again. Square roots in there? Multiply by the conjugate. Simplify, then substitute. Step 3. If x is heading off to infinity, forget the small stuff. Keep only the highest power on top, and the highest power on the bottom. That's your answer. 4 techniques. That's the entire toolkit for computing limits in this course. Practice these on a few problems, and they'll become second nature. You'll start spotting which tool to use the moment you read the question. Now in this video we learned how to compute limits, but we never really proved why this whole approaching idea works mathematically. What does it actually mean for x to get close to a number? In the next video we'll answer that with the rigorous definition of a limit, the formal one with epsilons and deltas. It looks intimidating at first, but once you see it, the entire foundation of calculus clicks into place. If this video helped, hit that like button and subscribe to Webronaq so you don't miss the next one. See you there.